Hello everyone, welcome to the mathematics in my channel. In this video we are going to solve this nice integral from 0 to pi over 4 tan of x natural log of tan of x dx. So how to begin? Well, first I'm going to define an integral. J of n is equal to integral from 0 to pi over 4 tan raised to the n power of x dx. Then I'm going to differentiate with respect to n. So we have j dash of n is equal to here 0 to 5 over 4. So if we differentiate with respect to n, we have here tan raised to the n power of x times natural log of tan of x dx. Then instead of n, if we plug in 1, we have j dash of 1 is equal to integral from 0 to pi over 4 here tan of x times natural log of tan of x dx. Now this is our integral I. So we know now I is equal to j dash of 1. So let's evaluate j dash of 1. So we know now j of n is equal to integral from 0 to pi over 4 tan raised to the n power of x dx. Then I'm going to take a substitution. T is equal to tan of x. Then if we differentiate, we have dt is equal to secant square of x dx. Then dt is equal to secant square of x, we know 1 plus tan square of x, so tan square of x t square here times dx. So we can plug in. Now limit we know 0 to 5 over 4, tan of 5 over 4 we have 1. Then tan x we know t, so we have t to the n. Dx we have here dx dt over 1 plus t square, so 1 plus t square times here dt. Okay, now this integral familiar with us because before 3 or 4 days we solved this integral. We generalized this integral from 0 to 1 x to the m over 1 plus x to the n dx is equal to 1 over 2 times n digamma of m plus n plus 1 over 2n minus digamma of m plus 1 over 2 times n. Okay, now comparing with our integral, we know m is equal n, and also we know n greater than to minus 1 and n is equal 2. So we can write here this is equal to 1 over 2 times n is equal to, so 1 over 4 digamma of m plus n plus 1, so n plus 2 plus 1, so n plus 3 over 4, n plus 3 over 4 minus digamma of n plus 1 over 4. Well, then I'm going to differentiate with respect to n. So we have j dash of n is equal to, now in differentiation we should multiply by the coefficient of the variable. So the coefficient is equal to 1 over 4. So here 1 over 4 times 1 over 4, 1 over 16. If we differentiate digamma function, we have trigamma function. So we have trigamma of n plus 3 over 4 minus trigamma of n plus 1 over 4. So now we know our integral I is equal to j dash of 1. So I is equal to j dash of 1. Then here 1 over 16. Here we have trigamma of now n we know 1, so trigamma of 1 minus trigamma of here 2 over 4, so 1 half. Well, now we should find the value of trigamma of 1 and trigamma of 1 half. So let's consider the series representation of trigamma function. We know n is equal 0 to infinity 1 over c plus n perfect square. Then we need to trigamma of 1. So trigamma of 1 is equal to sum of 0 to infinity 1 over here n plus 1 perfect square, and we know this is just Riemann zeta function. So here we have zeta of 2, and zeta of 2 we know 5 square over 6. Then also we should find the value of trigamma of 1/2. So let's call the reflection formula of trigamma function. We know trigamma of 1 minus c, then plus trigamma of c is equal to pi square over sine square of pi times c. Okay, then if we plug in 1/2 for c, here trigamma of 1/2, here again trigamma of 1/2 is equal to, here we have 5 square. Then we can isolate the trigamma of 1/2. We know trigamma of 1/2 is equal to 5 square over 2. So we can plug in here 1 over 16. Trigamma of 1, we know 5 square over 6 minus trigamma of 1/2, 5 square over 2, 5 square over 2. So if we simplify, we have minus 5 square over 48. Okay, this is the answer for our integral. If you like this type of videos, please subscribe this channel. Thank you for watching.